Set to go. All right. Good afternoon, morning to everyone, and thanks so much for tuning in. I'm Nat Quinn, and I have a master's degree in data visualization and analysis from Pratt Institute, and a bachelor degree in environmental science and studio art from Colorado College. This summer, I worked with the Open Topography team to create a new Open Topography tool and a couple of Jupyter notebooks to visualize LiDAR and DEM data available through the Open Topography portal. So overviewing the three projects I completed this summer. The first is a new tool currently in beta on our Open Topography website. This tool generates contour lines from Open Topography DEM or Digital Elevation Models product. And the next two are Jupyter notebooks posted in the Open Topography GitHub. The first one creates and exports 3D surface meshes from LiDAR datasets. And the second, creating realistic renderings of landscapes by projecting satellite imagery onto the three-dimensional models. So first, let's discuss the contour line generation tool. As mentioned before, this is currently in beta and will be released in the next few weeks on the public-facing website. So the contour line tool starts with the Open Topography DEM generation tool. So this generates a raster DEM from point cloud datasets. From there, the DEM is passed through a Gaussian smoothing module. This step is critical to generate kind of smooth and consistent contour lines. We'll discuss this more in the next slide. Then finally, the smooth DEM is passed to the GDAL contour command, which produces contour lines up to 0.1 meter in resolution. These contours can be downloaded as a shapefile, VEAP, or GeoPackage. So regarding kind of that middle step there, the smoothing module, we use a Gaussian filter, which can be adjusted by the user with the radius and sigma variables. And as seen kind of in that above user interface, we have a default setting that works in many, if not most cases. However, allow users to adjust as needed in the drop-down menus. The reason we pass the first original DEM through the smoothing module can be seen kind of in those two bottom images. So LiDAR data is often kind of too detailed to produce the shapes we typically associate or need for contour line usage. And so for this reason, the smoothing module produces contour lines that don't kink and are within the margin of error of the data itself. So here is an example of the output contour line generation tool. As you can see here, the lines are quite smooth and they're ready for a variety of use cases that all sorts of different research and different uses all over the board there. Okay, so the next notebook produces a 3D surface mesh from LiDAR datasets. So these can be opened in an STL file format that can be opened in a variety of 3D modeling softwares, and that's downloaded directly from the notebook. And this notebook can be accessed on our Open Topography GitHub. So to create a 3D mesh, the first step is to subset or thin the point cloud dataset. Using the entirety of a point cloud data set is kind of unnecessary for most renderings and quite computationally intensive, slowing the modeling speeds dramatically. So to thin that data set, we use a voxel cubic grid, which is applied across the spatial extents of the original point cloud. So that point, so basically that point that is closest to the barycenter of each voxel grid is used to represent all the points within that cube, that voxel cube. The degree of thinning is dictated by this voxel cube size, meaning larger cubes contain more points, and then a single point represents more data from the original point cloud, lowering its resolution. So those kinds of, that's the balance that different use cases and different spatial extents, you can kind of have that feature and you can change that parameter inside of the code itself. After the point cloud is thinned, then it has a triangulated mesh computed. And these facets are created between all the points, and then the planes are joined to form the mesh. So here are a few of the outputs. So here are a few examples of 3D surface meshes. The top left and then the right image are black wireframes that show the form itself, while the bottom left image begins to show how we can render these meshes. In this case, this is just rendered with a single color, but there's a digital lighting source that produces the shadows. So this kind of brings in the idea of like adding materiality to these meshes. Which brings us to the final Jupyter notebook, which creates realistic landscape 3D model renderings using the Ray Shader library in R. So this notebook calls the USGS 3D LiDAR API and a 1 meter resolution satellite imagery API to produce these renderings. Users can input their spatial extents within the continental United States and produce their desired rendering of the input bounding box. So just to kind of have a visual look at how this works. So these renderings are created by the projecting that 1 meter resolution satellite image seen at the top there onto the 3D elevation model, the form in the middle, to create the final 3D landscape rendering at the bottom. The rendering is output on an XYZ axis, so it can be viewed by whatever angle is desired by the user. So here are a few examples that came directly out of the Jupyter notebook. This one is of Mount Hood in Oregon. So you can see how the viewing angle can be adjusted depending on the needs, whether you want a perspective shot or an elevation shot. Obviously, however you want to orient, you can do that to produce the images. This rendering is of Canyonlands National Park in Utah. So as you can see, the spatial extents of a rendering can be quite large or small, depending on the detail needed for your particular output image. Then on top of that, there's a variety of sort of visual effects one can do to that image, right inside of Ray Shader itself and inside of the notebook. So this one applies kind of a softer, warmer lighting to the Grand Teton in Wyoming. Again, that's sort of all user based and whatever kind of effect you want to have and what you want to be showing. So in the final rendering here, so these two renderings are of Crested Butte, Colorado. They kind of show the potential of using this in sort of a town planning or town imagery that can be used for kind of urban planning processes. It's like you can start to see how using this as your base and then starting to produce some overlays on top, you could explain a variety of different proposals throughout the town. And then this final one, so this is the idea of the overlays comes up in this graphic and how we can start to use these renderings in a more concrete way. So here, the water level line graph of Lake Powell from 1998 to 2021 is really brought to life with the addition of these realistic renderings. The power of the imagery communication tells the same story as the line graph it references. However, a much more kind of visceral feeling of the change to the viewer. So this graphic was created using kind of both of those last two notebooks, as the rendering is produced in the Ray Shader notebook, and then the modeled historic water level, the 1998 graphic there on the left, is calculated by bringing the 3D surface mesh into a modeling software and then building the new water line and calculating it, and then creating that new water line and volumetric water showing. And then at the end, all of this is combined kind of and laid out in Illustrator. So I want to give a huge thank you to both Chris Crosby and Matt Beckley, who really stuck with me, and I really appreciate how much freedom they gave me and also full support throughout this entire summer. Also the rest of the Open Topography team for supporting my work, the NSF, as well as Anika and Kelsey, and thanks to all of the staff at UNAVCO who graciously invited us into your world. And I will take whatever questions you all have.
Great job, Nat. So you can either unmute yourself and raise your hand, or you can type your question into the chat. And I'll read it for you. Donna has a question. She would like to know if you can share how these materials will be disseminated and advertised with quotation marks.
Sure. So, kind of going through, so the contour tool will be available on the Open Topography website. It's currently in beta. It will be released to the public probably within the next few weeks. And then the other two notebooks, the one that's the ray shader, so the kind of the rendering one, as well as the 3D surface mesh, those two notebooks are on the Open Topography GitHub currently, so you can access them right there.
Great. Can I just ask a follow-up to that?
Sure.
So, and maybe this is a question for Chris, but like, so did you guys do like a promotion through the community, through social media, or through an email blast? Like, how are people going to know that they're on the website?
Yeah, so the kind of social media and blog post releasing is happening. Kind of a lot of this stuff got tied up in the last couple of weeks, so we're going to kind of release that through Twitter and Instagram, and that information will be available to all.
Yeah.
Great, thanks.
Yes. So Nat wrote blog posts about both of those notebooks. So we'll sort of with some of these nice images that are in this presentation. So we'll make those blog posts public, and then we'll promote them on various channels like social media and other places.
Great. And then
UNAVCO can retweet them. Hopefully.
I was just going to say we can amplify them.
Yeah.
Shelly, you can ask your question.
Yeah, so great presentation, great work this summer. This is just so exciting to see. And thinking about like how to use the Jupyter notebooks in maybe a less tech savvy community. And maybe this is a Chris question, but I know you can run Jupyter notebooks on your computer. Do we have our own like Jupyter notebook server so that someone could run it online?
Yeah, so first, these notebooks were both set up hopefully to be as user-friendly as possible. There's quite a few notes throughout them to kind of explain what's happening, why it's happening. That being said, I'm sure there are issues that come up with dependencies and installed libraries. Those questions will come up, and I think we'll try to address those as time goes on and add them in. The Jupyter notebooks they run in a browser, so you don't, when you essentially open it up, it will have essentially a little play button, so you can click that section of code. You do need to like add in parameters. Well, to start with the mesh one, you need to add in the parameters of your file path for what your original LiDAR set is. And then in regards to the ray shader notebook, there's two ways to access that. So it's technically an R library. So it's recommended to use RStudio. You can also run it in a Jupyter notebook, it's running R behind the scenes, but it was originally written in RStudio.
Oh, that's great. I mean, just a few years ago, running Jupyter notebooks, in a classroom environment was kind of scary. So it's so great to see like how easy things have become.
Well, we'll
wonderful work.
Report back.
And I'll just chime in. I'll chime in and say that actually the work that Nat did to build these Jupyter notebooks is ultimately we may take some of these other tools, especially the meshing tool, and actually turn that into a function that can be run through the web browser and Open Topography as well. So this was sort of a prototype for something that may get implemented in production Open Topo, which would make it a lot easier to use, obviously, because Jupyter does have a little bit of learning curve. We could also package these on Binder. I don't know if anybody's played with Binder, but it's sort of like Google Colab, which Levi just commented on the chat. But Binder would make it possible to run these as well, which we just haven't gotten around to building a Binder version of these yet.
Great, thank you.